In this video, we want to talk about measurable functions. And in order to talk about measurable functions, we'll need to talk about measurable spaces, measurable sets, and sigma-algebras, all of which we will define and explain in detail. So let's get started. This is the definition of a measurable function. Now, the whole point of a video like this is that that looks really complicated, and we want to get a handle on what all this stuff means. So let's go through it step by step. Okay, so the first sentence here, we have let omega 1 a1, so that's a pair, and the pair omega 2 a2 be measurable spaces. Okay, so let's talk about what measurable spaces are. So we have a pair here. Let's say we have a pair omega and calligraphic A, and I want to know when that's a measurable space. So this omega here is just a set, just some set. It could be the set of numbers between 1 and 3. It could be the real numbers. It could be a sheep head, a cow head, and a fish fin, right? It could be anything. Now, what is this? This second member of the pair here is a family of subsets of this set here. We'll call this the base set. And it has to have specific characteristics. So let's write that this way. So this A is a subset of the power set of omega. So you can look at this base set and think of a whole lot of subsets that omega has, and we're just talking about subsets like that. Subsets of omega. A is a collection or a family of subsets of omega. But again, this A has to have some specific qualities in order to qualify as a measurable space. It has to be a sigma algebra. So let's take a specific example of an omega and an A, and let's see, well, actually let's take a specific example of an omega and see if we can come up with an A that fulfills the characteristic of a sigma algebra. So we say that a family of sets is a sigma algebra if it has these three characteristics. It contains the base set, so in our case that's going to be omega. It's closed under complements, and it's closed under countable unions. So if this is our base set, and we'll take that as an example, let's see if any of these here are sigma algebras. That is, if we could use them as the second member of that pair to qualify as a measurable space. Okay, is this here a sigma algebra? So does it contain the base set? No. The base set is omega. Omega itself contains the members A, B, C, and D, and A itself does not contain omega. Omega is not here. And I also don't have a set written as A, B, C, D, right? So it's clear omega is not one of the subsets in this set. So that is not a sigma algebra. What about B? Does it contain the base set? Yes, it does. It contains omega. Is it closed under complements? Okay, well, what would be the complement of A and B with respect to omega? Well, it would be C and D, right? So, and that's in there, so that works. What would be the complement of C and D? Well, it would just be A and B, right? Those are the only two. These are the other two elements, so that would work. But what is the complement of omega with respect to omega? It would be the empty set, right? And this does not contain the empty set. So this is not a sigma algebra. What about C? Would this be a sigma algebra? Well, does it contain the base set? Yes, it does. Is it closed under complements? So the complement of A would be BCD, so that works. The complement of BCD would be A, that works. Complement of B would be ACD, that works. And it turns out that all of these work. The complement of omega, with respect to omega, would just be the empty set again, as we just saw, and that is here this time. And the complement of the empty set is omega itself, so doing well. So we have the base set. It's closed under complements. Is it closed under countable unions? Well, if I put A together with B, C, and D, so in other words, A union set with B, C, D, yeah, then I get omega, and omega's in there, so that would work. Well, what if I put A together with B into a set? Well, then I get the set AB, right? And that is not in here. So again, this is not a sigma algebra. In other words, you could not use this set as the second in a pair to have a measurable space. And you couldn't use this one either, you couldn't use this one either. So we're looking for something here that will work to qualify as a measurable space. And we see that it's not self-evident the way it is. Maybe you can't look at these and just automatically see that they're not sigma algebras. So let's continue our search if we can find something that will qualify our pair as a measurable space. Is this a sigma algebra? Okay, does it contain the base set? Yes, it does. Is it closed under complements? So the complement of AB would be CD, right? The complement of CD would be AB, so that works. And as we saw before, the complement of omega itself is the empty set, and the complement of the empty set is omega itself, so that works. And is it closed under countable unions? In other words, can I make unions out of all of these and still stay in the set? Okay, so if I take these all together, I just get omega itself. If I take these together, I just get the set itself again. If I take these together, I get the set. It turns out that I can take any of these that I want together, and indeed I stay within the set. So this is also closed under countable unions, and the countable just means that even if we had infinitely many elements here, I mean here we only have 1, 2, 3, 4, we only have 4 elements, right? It's a finite number. Even if we had an infinite number of elements, we could still take a countable union of all of those. In other words, we can have as many elements here as are in the natural numbers, take the union of them, and they would still have to be within this set here in order to qualify as a sigma algebra. Okay, so not only finite unions but also countable unions. But here, since we're only dealing with finite sets, that's not going to be a concern of ours. Okay, now we have indeed found a sigma algebra. What about this one here? Now this is an interesting case, this set E, because it is actually the power set of omega. And it turns out that the power set will always be a sigma algebra. Let's see why. Well, does it contain the base set? Well, of course it's going to contain the base set, because the base set, so omega itself, is also a subset of omega. And since this, being the power set, is just the set of all the subsets of omega, well then, in particular, it will also contain the base set. Now, is it closed under complements? In other words, can I combine any of these? For example, I'll combine B and C into this set containing B and C. Well, whatever I get through doing that, it's going to be a subset of omega, right? And I have all of the subsets here, so obviously that's going to be in it, and you can see that right here. BC is obviously in there. Okay, what about unions? Sorry, that's what we just did unions. Now we need to know about the complements. So anything that I take. Let's take ABC. Let's see, what is ABC without without C, right? So A, B, C without C. Well, whatever that ends up being, and in this case it just turns out to be AB, which we have here, we're obviously going to end up with the subset of omega, right? Whatever we do, whatever sort of complements we do. So we're never going to go outside of this power set. So this is always going to be a sigma algebra. Okay, so now we have gotten through this first sentence here. We know what we would have to do in order to have a measurable space. We just have to have a pair, the first element of which is any old set, and the next one has to be a sigma algebra. And this sigma algebra itself has these specific characteristics. Now there's one other thing that we haven't talked about yet. We've talked about measurable spaces. We've talked about sigma algebras. Measurable sets are easy. Those are just the sets inside of a sigma algebra in one of these pairs in a measurable space. So this here is the base set, or the universal set. This whole thing is called a measurable space, and the sets in this set here are called measurable sets. Okay, so now we can get to the point of this video, which was measurable functions. So a measurable function from omega 1 to omega 2, or sorry, I'm getting ahead of myself, a function f from omega 1 to omega 2 is said to be a1, a2 measurable if this condition here holds. So before we get to the condition, let's just make up a function from omega 1 to omega 2. So let's take this here as omega 1, so the set containing A, B, C, and D, and we'll take this as the sigma algebra in the measurable space. So in other words, our measurable space was omega 1, A1, right? This is that pair there. And this is the pair omega 2, A2 in our example, and this is indeed a sigma algebra. Okay, so let's just make up some function. Let's say A goes to 1, B goes to 2, C goes to 3, and where does D go? Let's say D goes to 3 as well. Okay, now what do you think? Is that a measurable function? I don't know. Let's find out. So what's the condition that we would have to check? So if the pre-image of all A2 and A2, so what does that mean? So the pre-image of all of these here. So we're going to have to look at the measurable sets in A2 and make sure that their pre-image has some specific characteristic. So the pre-image of, let's just start here with 1, is going to have to be, what characteristic is it going to have? The pre-image of all A2 and A2 under F is in A1. Okay, so whatever the pre-image is, it's going to have to be in here if I want it to be a measurable set. So what is the pre-image of the set containing 1? In other words, what elements get sent to 1? Well, here just the element A gets sent to 1, so the pre-image is a set just containing the element A. Now, what I need to know is if that is in A1. Is it? Is this A in A1? No, it's not. right? We have AB, we have CD, we have omega 1 itself, and we have the empty set. That's not in it. So, right off the bat, we've determined this is not a measurable function. And no need to be surprised about it, because we just made up some random thing, right? Obviously, a measurable function has to have some sort of interesting characteristics, has to fulfill some sort of prerequisites in order to qualify. So maybe we have to think about this a little bit more. Let's see if we can create a measurable function. Well, what would happen if we change this definition up a little bit? Let's say we sent A to 1 and B to 1 and maybe C to 2 and maybe D also gets sent to 2. Okay, so nothing's been sent to 3, but no one told us this had to be a surjective function, right? So we'll call this F. Let's see if that is perhaps a measurable function. Okay, so we just need to check all of these, right? We don't need to check these, right? Remember, we're not looking at these. We just need to check each one of these, all of these measurable sets in A2, and see if their pre-image is indeed over here. So what is the pre-image? And maybe we should write what the pre-image means. So let's go through that as well. What is actually technically and notationally the pre-image? So the pre-image is actually just all of the members of omega 1, right, for whom it is the case that f of x is in this set A2. Right? Okay, so let's search out these pre-images for each element. So what is the pre-image of 1? In other words, what elements get sent to 1? Oh, well, A and B both get sent to 1. Now, the moment of truth. Is the set that contains A and B in this set over here? Yes, it is. Okay, very good. So that is in calligraphic A1. So far so good. Now, what is the pre-image of, we have to look at the next one here, the set containing 2 and 3. In other words, what gets sent to 2 and 3? Well, nothing gets sent to 3, so we don't need to concern ourselves with that. What gets sent to 2? So C and D gets sent to 2. Now, is that in our set A1? Yes, it is. Okay, so far so good. What about 2? Let's do this a little bit more quickly now. 2, what gets sent to 2? Well, the only ones that get sent to 2 are C and D, right? And we already saw that that's in the set, so that'll work. And the next one we need to check is 1 and 3. So what gets sent to 1 and 3? Well, again, nothing gets sent to 3, so that's not interesting to us. What gets sent to 1? A and B. Well, we already saw that A and B are in our set, so far so good. What gets sent to 3? Actually, just the empty set gets sent to 3, right? Nothing. The pre-image of the set containing 3 would just be the empty set. And is that in our set calligraphic A1? Yes, it is. Okay, so far so good. What about 1 and 2? What gets sent to either 1 or 2? So the pre-image of the set containing 1 or 2, or 1 and 2, is, so what gets sent to 1? A and B. What gets sent to 2? C and D. So we get A, B, C, and D, right? So that's just omega 1 itself, which is there. Very good. Okay, well, what about omega 2 itself? What gets sent to omega 2? Well, in other words, all of these get sent to somewhere within omega 2. So again, the pre-image would be omega 1. And what gets sent to absolutely nothing? Well, nothing, right? So the pre-image of the empty set, well, is the empty set itself, right? So that's in there. So that is apparently a measurable function. We have found a measurable function. And at this point, it might be interesting to see that sometimes it's very easy to know whether something's a measurable function. Let's look at this example here. Now I'm just going to close my eyes and make up something here. Now I want to know if this is a measurable function. And I'm going to say, yes, that's a measurable function. And I already know that it is. Now, how do I know that? And here's the way I know that. What am I going to have to do? Remember that checking whether something is a measurable function or not always means looking at all the elements over here. Right? That's what it means. I want to see what is the pre-image of one of these. I'm just going to write a normal A2 here, so that could stand for any one of these here. Well, without having specified which one of these I'm talking about, I don't know exactly what the pre-image is going to be, but I definitely know that the pre-image is going to be some subset of omega 1 here, right? Because I'm sending each one of these over to something. So I'm going to get some subset of omega 1, right? Let's call that small omega. Now the question is this small omega in A1 or not? Well, it turns out A1 is just the power set of omega 1. Right? These are all the possible combinations of subsets of this here. I didn't mention that before, of course, but as it turns out, that's the way it is. So it turns out whatever this small omega here is, it's going to be some subset of omega 1, and all of these subsets of omega 1 are in there. So it must be in the set, and thereby it must be a measurable function. So now let's look back at the very beginning and see if we can understand this thing that before looked so complicated. So let omega 1 A1 as a pair and the pair omega 2 A2 be measurable spaces. That just means that this is any old set and this is a subset of the power set of omega 1 that has specific characteristics, meaning it is a sigma algebra. And then we have some function between these two sets here, and we say that that is A1, A2 measurable if the pre-image of all of the measurable sets in here under F is inside of A1. And we saw that, at least in those cases we were looking at, this was not in principle difficult to do. And then it was written out here in this mathematical notation. All we're saying there is that the pre-image of all the A2s, so of all the A2s in the calligraphic A2 here, the pre-image, and this is just the definition of pre-image, that's all that is in A1. So that was a video about measurable functions, and I hope it helped you.